Today we're going to talk about the iterated integrals over the rectangular regions, and then also try to generalize that to more general regions. So what we'll do is we'll take a look at our special function. And we'll take a look at a square region below our special function. Where x goes from a to b, and then y goes from c to d. And so when we take a look at this, we're looking at a double integral. We can call this region R for now, so let me set this up in a couple of different ways. A double integral that's integrating over R. And my function with a differential dA, where A, as you remember from last time, is the change in area. It actually is going to refer back to the dx dy or dy dx. So we could take a look at this as the volume under this region, under the curve over this region that we're computing. And then we can set this up as an integral that looks like an integral of the function with respect to x. If we decide we're going to integrate with respect to x first, then the x limits are going to be from a to b, and then we integrate with respect to y, where the y limits are from c to d. And it turns out for this special scenario, we can also take a look at this integral where, for some reason, if we wanted to integrate with respect to y first, dy, and so our inner integrals will be from c to d, and then your dx integrals, your outer integrals, will be from a to b. Yes? For this particular example, it's just nothing. It's a square, it's a rectangular region. So for rectangular regions, it turns out that whatever works for you would be fine. So why would we want to switch the order of integration? That's a couple of things where you might want to do that. One, you might be interested in switching the order of integration because your region is not a rectangular region, and one way would be easier than another. And we'll see examples of that hopefully by the end of today. Another reason for switching the order of integration is that if you integrate with respect to one variable first, the integral might actually be impossible to integrate using our techniques from Calc 2. And we'll see examples of that as well. All right, but just to try to get a visual of this, if we integrate with respect to x first, what we're doing is we're essentially fixing our y values. So if we integrate with respect to x first, then we're going to integrate from A to B, which means we're going to fix the y value somewhere, and we would probably fix it somewhere between what we're integrating over, between C and D. And what we're doing is, when you integrate this, you might still get something with a function of y in it, because you're holding y constant. And what you're saying is that you're going to integrate with the y being constant. And so what you're getting is you're getting a slice. You're getting an area of a slice of this volume from A to B. You're integrating from A to B where y is fixed, so you're getting an area there. So now you have an area function as a function of y, and then you integrate that from C to D, and then you would find this whole volume. Okay? You've done this before in Calc 2, where you found a volume of something, except you don't look at it as a double integral, of course, because you're not looking at it as a function of x and y. But you have done something similar to this before. Yeah?
Are you talking about rotation around the x and y axis?
We can think about the rotation. Yeah, you're doing circles. You're getting areas of circles, and you're adding up those areas together. So in our case, this is not a circle, but you can think about this as those areas of circles that you're going to add up, stacking along the x or the y, or depending on how you rotate. Yeah.
So then that would mean that some of these double integrals you can actually put all into one, integrate under just one thing.
Well, after you take this first step of integrating with respect to one variable first. After you do this, it becomes a single integral.
But when we were doing rotation, we just did the integral under just one thing.
Yes.
In terms of one thing. So are you saying that we already did this beginning step, this first step, and then we put it all into one when we were doing rotation?
More or less, yeah.
Okay.
Yeah, that first step where you have to try to figure out it's a rotation, so it's a washer, or it's a disk, right? So when you say it's a washer or it's a disk, then you're finding this area function,
Okay.
and then you're going to integrate. But people who learned this a while ago think of this as the sliced bread method, because what we're doing is after you're figuring out the area of a slice, you're going to add up a whole bunch of slices. And then eventually get a volume out of that. So this was the next best thing since sliced bread. So you can see pictures of this, and I suppose I have a picture as well. If I could find it real quick. You know, this part really is not that important in terms of what you eventually need to know. I think this is just interesting theoretical stuff that would be nice to know. Especially when you tell your kids bedtime stories about calculus. So here's the example of, here's my example of the surface and its region, and what happens when the region's projected up onto the surface, and I get this piece of the surface. And so all the area under there, or the space under there, is going to be the volume that I'm actually computing. And if I do a slice, and there's a typical slice of an area that I would look for, along the, it looks like I sliced along the x-axis, so I'm fixing x and I'm integrating with respect to y first in this problem. And then here's the other slice, and I think I have them stacked up where I have a bunch of slices stacked up. So here's all the slices along one direction, or you can imagine how the slices would go along the other direction as well. All right, so that's a general overview, pictures and stuff. Let's take the box out so I can take a picture of this. That a good picture? Okay, so let's actually do the computations and then talk about general regions where it is going to be, the order of the thing is going to be important. Let's see. So I was looking at this one. I hope this wasn't too hard. So let's calculate this double integral. So it starts off with a double integral over a region, R, and then this is your you're integrating over this domain. And to try to picture this in 3 dimensions is kind of difficult, so the best thing to do is to look at the region portion of it and then worry about what happens in 3D somewhere else. So if you have a graphing program, then that's great, you can do that, but if not, then your main focus is what's happening in R. So our R goes from 0 to 2 and Y goes from 0 to 1, so it's a nice rectangular region. So we're asked to calculate the double integral. So if we do the double integral, we have the double integral of 10, 1 plus x squared over 1 plus y squared dA. Now, I can decide at this point whether I should integrate with respect to x or with respect to y first. And for these rectangular regions, again, it really doesn't matter. So let's do it with respect to x first. That means the inner integral will have the x limits of 0 and 2. And then you integrate with respect to y, and that has y limits from 0 to 1. And so some people actually do this separately and then put it back in here. So it's up to you how you want to approach this. But we could think about integrating from 0 to 2 off to the side. With respect to x, so anything with a y in it can get taken out, right? You see that everything with a y in it is constant. So I can almost, not almost, I can just take the stuff with a y in it out of the integral and just integrate with respect. All right, now what? So I would have 1 plus x squared here, dx, and then everything else was constant. Is that right now? Okay. And so this makes for a fairly easy integral, I think. We're going to say x plus x cubed over 3, evaluate from 0 to 2. And 0's gone, so I'll have 2 plus 8/3, which could be 14/3. Yeah, 14 thirds. So multiply by this down here, I'm going to get 140 over 3 times 1 over 1 plus y squared. Okay? So you could have done it down here, right below, but I decided to do this off to the side. And then now that I have my answer for this, I'll put that in here. And so my second integral is going to be from 0 to 1, 140 over 3 times 1 over 1 plus y squared dy. And the reason why I wrote it like this is that 140 over 3 is a constant. I can just take that out. So that's one part of the integral. The second part of the integral is the outer integral with respect to y. So 140 over 3. And then the integral of 1 over y squared, 1 over 1 plus y squared is the arctan. Arctan of y, my y limits go from 0 to 1. And so arctan of 1. You know what the arctan of 1 is? So 140 over 3 pi over 4. I suppose that would cancel 70, 35. Okay. It should be. Let's take a look at it. So it's 35 pi over 3. Okay, looks good. What? Yes. What happened? All right. So I think I would expect you in a test situation, expect you to be able to do basic integrals like this. And in homework, they'll probably expect you to be able to do integration by parts, maybe some trig sub or partial fractions or whatever. But you know, if you don't have to show your work, you can just plug it into Wolfram Alpha and get the results, and I don't care. All right? Because I'm not going to teach you how to do integrals. You're here because you passed Calc 2. So somebody said you can do integrals. I'll just trust that. All right, let's take a look at another problem. This time I'm going to grab one from the book. One of these guys. The red one. Number 19?
Yeah.
Oh, number 9, the video that was playing right before us did something similar to number 9. Let's do number 19 then. It's a cross, but it's not the cross product, right? It's x by y, so limits for x and limits for y. So again, the setup is a double integral over a region. This is your region, and again, the important drawing part for you is not the three-dimensional volume of this thing, although if you can draw that, then good for you. If not, then you really should just focus on drawing this on the x and y axis. So here are your x values and then your y values. So your x goes from 0 to pi over 6. And then your y goes from 0 to pi over 3. And at this point, the only thing that's important really to gather from this information is that you have a rectangular region. All right, so we can decide what to integrate with respect to first. And do you have a preference just by looking at the integrand, what's inside of the integral? Would you have a preference for this? Yeah, maybe y first, so I could treat x as a constant, and then I'll deal with x later on. So that's probably a good move. Let's go with respect to y first. So integrate with respect to y first, x sine x plus y dy. And now if I look at my y values, my y goes from 0 to pi over 3. And then dx goes from 0 to pi over 6. So let's focus on the inner integral, iterated. You're iterating from inside out. So let's go and integrate this. So this is really just a sine x, right? Do a u substitution, it'll be a sine u or something like that. If that makes you feel better, let's do that. U equals x plus y with respect to y, du is going to equal to dy, so that's nice. There's no extra stuff happening. So x is a constant. We have sine u du. We integrate sine. What's the integral of sine? Negative cosine. And then u is x plus y, so let's just put that in there already. Now, this 0 to pi over 3, remember, is the value that you're putting in for the y. So in the first problem, the first example that we didn't kind of got rid of the y's and put it outside, all the way outside, while we integrated with respect to x. So this time, the x's and the y's are still present here. And so just for your own sake, for my sake, I usually put down the value of the variable that I'm putting the numbers in, just so I don't confuse myself. So I know I'm going to put 0 and pi over 3 in for y, not x. So I have a minus x, cosine of x plus pi over 3, plus, or let's just call it a minus, and then a negative x again, cosine of x plus 0. So here is my first integral, the inner integral. All right, now I bring all this other stuff down, which is really just an integral sign from 0 to pi over 6 dx. And so now I know I'm going to integrate this with respect to x. And this integral requires integration by parts, which I won't bother with because I have Mathematica. So let's just integrate this. Let's integrate. I'm going to put the whole thing here kind of blindly without simplifying. Minus x cosine of x plus pi over 3. I'll simplify the minus minus and call that a plus. X times cosine of x. Then I'm integrating this for x values going from 0 to pi over 6. So there's my answer. Then I'm done. Okay. Questions? Stuff's really easy, huh? All right, so let's take more steps. And now, instead of looking at, let's see if there's anything interesting here. Oh, let's do one where they're actually looking for a volume between surfaces. Let's the red ones. Number 27. Find the volume of a solid under the elliptic paraboloid that and above the rectangle from -1 to 1, -2 to 2. All right. That. What is that? That is a surface that, that can be described as a function. So the double integrals that we're dealing with are z is equal to f of x, y functions. Those are the functions that go inside of the integral. So those are the integrands. So first thing that we probably would like to do is express this as z is equal to f of x, y by getting z by itself. So if we get z by itself, we're going to get 1 minus x to the 4th, or x squared over 4 minus y squared over 9. Which, according to them, is looking like an elliptic paraboloid. And so by looking at this, can you tell how the elliptic paraboloid looks like? Longer along the y-axis. The ellipses are when you make your cuts, but this is, the bottom line is this looks like a paraboloid of some sort, which means what? Open up or down? Down. So it opens downward, and the slices are going to be those ellipses that are longer along the y. So you don't need to picture this, but I think it's a good exercise to try to imagine how this thing might look like. So the elliptic part of the paraboloid comes when you let z equal to constants, and then you'll have a paraboloid. So when z is equal to 0, for example, then you'll have this paraboloid where you have this ellipse. So let's, I don't know if I should keep going with this, but let me see how far I can get. When z is equal to 0, it's opening, it's crossing the y-axis at 3, the x-axis at 2, and then it has these ellipses, or it has this one ellipse at 0, and it's pointing downward. When x and y are both equal to 0, x and y are both equal to 0, I'm going to hit the z-axis, and so my z-intercept is going to be what? So just up by a level of 1, so it's just going to go upside down paraboloid from there. Okay, again, that picture is not important. Just to confuse this picture even more, what we're looking at is this region that's going from -1 to 1 in the x, and then -2 to 2 in the y. So you're getting this like dome-like figure, and you're trying to find that volume in there. All right. So Out of all this stuff that I did, I think the only thing that's important is that z. Now let's take a look at our region. Our region goes from -1 to 1 and -2 to 2, -1 to 1 in the x, -2 to 2 in the y. Oops. So it's a nice rectangular region. And so our integral, any preference, x or y? Integrate with respect to first. Doesn't matter. Let's do y first. So this is my function that I'm going to put in. I have a 1 minus x squared over 4 minus y squared over 9. And if I want to integrate with respect to y first, my limits are going to go between -2 and 2, because these are my y values. And then my x is going to go from -1 to 1. Okay? Now, an interesting thing about this particular problem is the idea of symmetry. And I think the book really stresses that idea of symmetry, where you could possibly simplify your integral quite a bit if you can see some symmetry in this. Now, the drawing, that awesome drawing, you can tell that there's symmetry in there. But without drawing, remember I said that's not really that important. Without the drawing, if you can look at the x's and y's and see that they're even, they're being squared, all right? And your limits are going from -2 to 2, -1 to 1. So you can kind of tell, not kind of tell, but if you can just, without visualizing the surface, you can take a look at the negative to a positive x value is going to be the same because we're squaring, I guess I said the x, right? So the -1 to +1 in the x can be trimmed down to just 0 to 1 and then double because the x is being squared, right? So we can actually chop the x down to, I'm going to do this in 2 steps, to 2 times going from 0 to 1 for the x. So by cutting this in half, knowing that your x limits are symmetric, we can double the integral from 0 to 1 instead of going from -1 to 1. Oh, yeah. Okay? And likewise, I can see the symmetry for the y as well. So I can multiply that by another 2. Using symmetry. Okay? So if that makes your integral a little bit easier, then you should try to take advantage of that. Otherwise, this is just as correct as the bottom one. Okay? All right, cool. Questions? Yes?
When would the volume of something be zero?
When half of the surface goes underneath. So just like in regular integrals in Calc 1, you know, the negative values, if your graph goes underneath, you're finding the area here, your integral will be negative. And so the same way for surfaces, if I extend this paraboloid to go down further, and then the volume under that paraboloid is equal to the volume that's outside, that's below, then it'll end up being 0. Yeah.
Can you do an example of the volume in between two surfaces?
Oh, okay.
I think that's a lot of stuff.
All right, so maybe something like 34. So we have two surfaces. We have z is equal to e to the negative x squared cosine x squared plus y squared, and then z is equal to 2 minus x squared minus y squared. And we want to go from x, absolute value of x less than 1, absolute value of y less than 1. So if you look at that region is actually, that square of negative 1 to 1. So we have our region, and then we have two surfaces. At this point, the only thing that's important is to try to figure out which surface is greater than the other. And so there's a few ways to do that. One way is to just pick a point, and 0, 0 seems to be a nice, easy point. Pick a point in this region and plug it into both surfaces and see which one gives you the larger surface. And so if I put 0 in for the first one, 0, 0, 0 for x, 0 for y. Into the first z, and I'm going to have 1 cosine of 0 is 1, so it's 1 times 1. So I'm going to get 1. If I put 0 in for the second one, I'm going to get 2 minus 0, so just 2. So it looks like this is going to be the larger of the two surfaces. So in my integral, I will just make sure that that's going to go first. Okay? So let's set up the integral. I'm going to integrate with respect to, it doesn't matter with respect to first. Let's just say integrate with respect to x. My first function is the larger function, 2 minus x squared minus y squared. And then the second function is my lesser function, e to the minus x squared cosine x squared plus y squared. And then I will integrate this with respect to, it doesn't matter, let's go with respect to x first from minus 1 to 1, and then with respect to y, from minus 1 to 1. Is there symmetry here? Just look at the function. So we haven't looked at the thing. There's symmetry for the first one? Is there symmetry for the second one?
Well, e to the negative is not symmetrical. The exponential functions aren't symmetrical.
What?
You can break up the integral though, right? Yeah, the first part of the integral, when you break it up, is.
Uh-huh. Is the second one?
The second part isn't.
Oh.
Oh, no. No.
I think it is. Right? Because it's symmetric. You guys are probably looking at symmetry around the whole thing to break it up into 1/4 of the integral. If you think about breaking this up, just the y from minus 1 to 1, make that go from 0 to 1 and double it. That looks like it's fairly symmetric. It's also symmetric along the y.
Oh, because e to the whatever is constant.
Because it's being, well, plus it's being squared, so it's symmetric along the x. So I think that's enough to be able to break this down into just just looking at the first octet. You can graph it.
Oh, okay, I believe it now. I just wanted to look it up.
So I don't know how strange this is going to be, because e to the x is going to squash the graph rather quickly. We'll see how this is going to look like. So it's e to the x negative, and then times cosine x squared plus y squared. Is that right? And let's just go from -1 because those are our limits. So there's symmetry in there. Well, this might actually be 0. Well, no, because we're doing the difference between two things. So yeah, maybe we should graph the other one. What was the other one?
3 minus x squared minus y squared.
What happened? That didn't look like the other one. Oh, maybe not. Okay, well, you're looking for that volume between these two things. And there is symmetry along the quadrants and stuff. All right, let's move on. Let's get past this stuff. Let's go into more general regions that aren't square or rectangular regions, because that's where it gets more interesting. Nor. All right, let's take a look at the more general regions, and let's make up a problem. Boy, that's dangerous. Huh? Let's make up a problem. Let's not. Let's just look at the book. Between 7 and 10, there's no reds. Let's do number 8. Oops. So we're integrating y over x to the 5th, y over x to the 5th plus 1. And then this time we have our region. They're calling it D now. So somewhere along the line they're going to be switching things up. So just like the rectangular region, or just like from the previous section we're dealing with, it's not important how the volume itself looks like. I mean, if you can draw the surface on some graphing program, then draw the surface on a graphing program, that'd be great. But what's important is what's happening on the xy plane in the region. So let's take a look at this, and this is something that you definitely need to be able to do, and this is something that you should have been doing back in Calc 2 when you're finding, volumes of revolution. Before you rotated about something, you had to draw the region first, right? And so this is going to be the same exercise. So our x goes from 0 to 1, and our y goes from 0 to x squared. So I'll graph my functions. My x is equal to 0, and x is equal to 1. Those are just those lines. And then I'll graph y is equal to 0, and y is equal to x squared. So between these four functions, or graphs, can you see where the region might be? So it looks like the region is going to be this little bit of graph over here, right? All right, let's blow this up just a tad bit. And label at least what's left over here. I don't know if I need to label the x is equal to 0, but x is equal to 1 looks like it's important to label. And then y is equal to 0, and y is equal to x squared. So these are the limits, or this is the drawing that I want you to have. So the way I want you to set this up is a thought process by looking at your drawing. Okay? In this particular example, it doesn't matter too much which one you want to integrate with respect to first, but the way they have the description of this thing set up, I think they would want you to integrate with respect to y first. Okay, so let's think about this. We're going to integrate with respect to y. So maybe I'll write this down off to the side as I'm thinking this through. Integrate with respect to WRT y first. Draw a line parallel to y-axis in the region. Yeah, you're thinking about drawing a slice. Okay? So parallel to the y-axis, and I want to be somewhere in the middle of the region. So I would draw a line, and I would notice that I would enter my region at some function. Enter region at y is equal to 0. So off to the side over here, I want to integrate with respect to y first. And I look at my drawing and I enter my region at y is equal to 0. I will be inside of the region, and then I note when or where I exit my region. Exit region at, now I'm integrating with respect to y first, so I need another equation, y equals to something, right? So I look, y equals to x squared. And so that's going to be the region that I'm going to get out of. So when you identify when you enter the region and where you exit the region, with functions, those two functions will be your lower and your upper limits for your y. Yes?
So if they actually integrate in terms of the other variable first, then when we integrate in terms of y, we would have to plug in an x squared again.
No,
Okay.
because so you're going to integrate with respect to x last, right? And I usually call this the outer limits of my integral, because in iterated integral I have my inner limits for the inner integral and my limits for the outer. So limits for outer integral are always constants. Okay? X goes from what to what? 0 to 1.
Because when you do it the other way, this was talking about is that you plug in, if you did it the other way, you would integrate in terms of x, and then when you integrate in terms of y, you're going to plug in another x, and you're like, well, I already integrated in terms of x. That was dumb. No?
Are y's going to be constants if you switch to order? Because the limits for outer integral are always constants.
That's why you can't do it the other way, though.
Oh, you can.
Can you?
Yes.
Oh, yeah. I'm excited now.
All right, so let's just write this integral out first. So then my integral is going to be, I'll start with writing my function y x to the 5th plus 1. And we decided we're going to integrate with respect to y first on the inside. And our limits for y are 0 to x squared. And then our outer limits with respect to x are always constants, 0 to 1.
Yeah.
Yes. Yes. Always. Okay, so when I give you guys a quiz sometime this week, your outer limits will be constants. Are you feeling me here?
How did you do it the other way? You just plug in like 1 for x squared?
Yeah, if for some reason you decide you want to do it the other way, let's see how that's going to look like. So if for some reason, and there could be a valid reason, that you wanted to integrate this with respect to y first, or x first. So with respect to x first, I would set up my xy limits like this. I want you to get used to doing this because, you know, for triple integrals, you'll have 3 of them. With respect to x first, I don't know if I can erase this. I can't erase it. I'll do it in red. With respect to x first, draw a line line parallel to x-axis, right? You note where you enter the region. And then you enter the region at some x equals 2 function. So let's see. Drawing the line parallel to the x-axis. Oh, here's where I enter the region. Right here. What is this function? This function is y is equal to x squared, but I need x by itself. So x is equal to the square root of y. So that is my into enter region, and then I note where I exit my region, and that's another x equals 2 function. So I'm in the region, la da 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 da, and then oh, here it goes. I'm exiting right here. X is equal to what? 1. So those are my lower and upper limits for my integration. What goes here? Constants. Constants go there. Always, always, always. Y, the y variable. The y goes from 0 to 1. Outer limits are always, always, always constants. So when you're on the quiz and for some reason you want to put down a function for your outer limit, stop yourself and listen. Always, always, always. Constants.
This sounds like a common error.
Right. Oh yeah, we could do that too. No. Always, always, always constant. That just means you could probably only do it. No, it's a valid question. You hear Ryan's question?
Yes.
Right? That just means that probably you can only do it one way. You can't switch the order. Or if you do, then it'll be a lot more complicated than it's worth. Okay? That's why. All right. Did you get that the outer limits are going to be constants? Okay. In statistics, when we do probabilities are always numbers between 0 and 1. And I tell students they're always, always, always between 0 and 1. And so I get answers like 2.5, 7.3. And then I just die a little bit inside. Isn't there a song like that? Just die just a little bit. 21? Oh, we didn't do the integral. Well, so my function. What was my function again? So I'm deciding I'm going to integrate with respect to x first, dx, going from the square root of y, 1, and then my dy going from 0 to 1. So if I were to try to integrate this with respect to x first, in here, I see I have to integrate 1 over x to the 5th plus 1 dy dx. Because the y is a constant, I can just leave it out there. And when I'm looking at that, I'm thinking, wow, that looks really hard. So what if I just stop here? Stop.
Was that a stop sign?
Oh, but it's in green, huh? Let's make the stop in red. Whoops. Okay. Let's go back to this one. I hope this is easier to compute. Let's take the integral with respect to y first. That's y squared over 2, right? And then x to the 5th plus 1 is constant. So it looks like my integral from 0 to x squared, the y is the 1 over x to the 5th plus 1 is constant, and I just have a y dy. So that's 1 over x to the 5th plus 1. It's y squared over 2, integrate from 0 to x squared. And if there's any confusion, you remember that you integrated with respect to y, so the limits will be y limits. And then you got 1 over x to the 5th plus 1, and then you put the x squared in, and that becomes x to the 4th over 2 minus 0 when you put 0 in for y. So you'll take that, put that in here. I'll rewrite this as a 1/2. X to the 4th goes in the numerator, and x to the 5th plus 1 goes in the denominator. Now I'm going to integrate with respect to x from 0 to 1. And I see that I can just simply take a u is equal to x to the 5th plus 1. du is going to be 5 x to the 4th dx. And there goes my easy integral. So in some cases, it will turn out that it'll be easier to integrate if you integrate with respect to one variable first than if you were to go do the other variable. So in the other case, we had to stop. It was impossible. But if we do it this way, it looks like there's a way to go. Should I finish this? So you got the 1/2 over here. This thing is going to be 1/5 du. Integral of du over u, because the whole denominator became u. So you get a 1/10 ln u. And I usually like to go back to the other stuff. So x to the 5th plus 1, and then I evaluate this now from 0 to 1. If I put 0 there, I get ln of 1, which is 0. So if I put 1 in there, I get ln of 2. And that's it. Okay. What happened? Did I miss something?
Yeah, so ln of 0 is like negative infinity.
Yeah, but there's a plus 1 there.
Oh, okay.
All right. So that was a good first problem. Or was that our second problem? That was a good second problem. Nate, that was our first problem, wasn't it? I don't know. All I know is that the outer limits are always, always, always constants. Oh my God, I'd be happy if you knew that.
Put this on that phrase.
Fill in the blank.
You know, I was thinking about it too. Always blank.
All right, let's do a couple of these where we're just going to set up the integrals. Having so much fun. All right, I guess we're out of time. We'll do that tomorrow. Just remember that outer limits are constants.